Yes, thanks for having me. Cool. So, you can tell I'm the geekiest in this room because I have my props and everything. I thought I would try and give you a glimpse of where the research world is headed in terms of robotics. So, to give you a bit of context, I'm part of a research team at Google that is focusing on the intersection of machine learning and robotics. And our goal is to try and see what the recent advances in machine learning can bring to robotics, in particular in bringing robots closer to the real world, to the human world, where things are not quite controlled, things are not quite as organized as you would have in an industrial or even a logistics setting. But in the human world that is, by definition, messy, complicated, with semantics that are very ambiguous and that are very hard to manage. So just to set the stage, in robotics in the last 30 years, there's one thing we've really mastered well, and it's the problem of actuating, of moving robots, right? The whole problem of planning, of motion, of control, and all of that has been remarkably well understood, and that's why robotics has really developed in industrial settings, and has really exploded in the past decades or so. Where the problem has been historically has been closing the loop with perception and sensing, right? All the work that has been done in computer vision, in visual understanding, has kind of fallen short, right? There is a lot of reasonably good understanding of the geometry of the world. The semantics were not there, and understanding the world is a really important part of closing this loop so that you can actuate and actually have a robot that works in the real world. I want to give you a quick case study to illustrate this point, and it's the problem of feeding robots. I discovered this relatively recently. What you see on the left here is a robot called Obi, which is designed to help people who can't feed themselves. And that it's a beautiful piece of hardware. It's very simple. Like, people can just program the arm to bring it to their mouth, and the robot will scoop food out of a tray and bring it to them. I've bought one. I have one in the office. It works extremely well. But you'll notice it's entirely open loop. In the sense, the robot doesn't have a sensing, doesn't have perception. The robot doesn't know where you are. It doesn't know what the food is in the tray. But despite of that, it's able to perform its function. Where we're headed, and this is a video from University of Washington that was demonstrated last year at NeurIPS, which is the biggest machine learning conference, is more of a closed-loop system where the robot is actually capable of seeing where the face of the person is, understand that the mouth is open, understand that there is food on the tray, sense the pressure of the fork on the plate, and close the loop and adapt itself based on that. So this is still very much kind of a prototype demonstration, but that's kind of giving you a glimpse of where people are trying to go, where you can actually have an end-to-end system that senses the world and reacts to it. So we've made a lot of really good progress in the last, I want to say, 3 to 4 years in the world of perception. And so we're getting closer to really closing that loop. The big changes has been deep learning. A lot of computer vision in the past was reasonably good at reasoning about geometry. Increasingly, deep learning is bringing semantics into the picture. Deep learning is neural networks, essentially, but scaled up. It enables you to take visual representations and interpret them and parse them and do semantic interpretation of them. It's been very successful in all sorts of tasks. Google Photos is a prime example of automatic labeling of what's in there. You can try it on food problems. If you want to get started, you can buy this AIY vision kit that's about $100. It's a little board with a camera on it. You can load it up with a dish classifier on it, which is a neural network, and point it at your food, and hopefully it will recognize what you have on your plate. It's a very simplified setting, but if you want to just get started with something like this, it's kind of a fun DIY experiment that you can make. there is a lot more research going on in that space right now. So, for example, this is at CVPR, which is the biggest computer vision conference in the one of this. There was one workshop started last year, and which is, I think, continuing this year, where people are challenging themselves to do parsing of food items on plates. So very fine-grained, very low level of detail of what the food is about and where it is. And I think this is going to continue because food is such a rich and complicated space to go into, right? And understanding cats versus dogs, that gets old after a while. Understanding really the fine details of this is a burger, this is a salad, and all that is a lot more difficult, challenging, and interesting for the research community. There's been also work on the act of cooking. So a lot of people have been building data sets of people actually in the process of cooking. So this is an example of egocentric videos of people actually preparing food and trying to understand what it means, what are the steps, and how do you interpret from a video what the different steps involved are, and trying to understand the process and hopefully replicate it in an automated way. So we're getting there. We have better perception. I want to argue there is one ingredient missing, which is that thus far, if you treat perception and actuation as two independent things, you're really putting a lot of pressure on both. Right? You really need to have really good actuation, really good precision of your control, and really good perception. Otherwise, the errors compound, essentially, and it becomes really hard to control your entire system. And that's been a challenge forever, that a little bit of drift in perception leads to drift in actuation, and so on and so forth. One thing that's happening recently, and that's sort of developing as an approach to solving the problem, is again using machine learning as a way to close the loop. And the idea there is that you don't treat perception and actuation separately. You optimize the entire thing end to end, such that you can reason about the position of your robots and the perception of the environment around the robots in one fell swoop. So to give you an example, this is work that we've been doing at Google. Those are arms that are being trained to pick up objects. So all they do all day long, those arms, is trying to pick up the objects that are in the bin. At the beginning, they're really dumb. They just go down and try to grasp things, and they mostly fail. And when they fail, we give them a negative reward. And then once in a while, by chance, they grab something, and then we give them a good positive reward on this. And they're all connected. They're all training a single big neural network that is essentially their collective brain. And we show them a whole bunch of objects, different textures, different colors, as wide a variety as we can. We're really trying to focus on the cases where the objects are not necessarily known in advance, and their texture might be very, they might be soft tissue, or they might be squishy, or they might have very weird shapes, so that they get the experience of basically handling any object possible. And the result is that we're able to pick up objects that we've never seen before very quickly and very reliably. What you see on the left here is an old version of the system that was the baseline that we started from. On the right is our most recent system, which basically nails the task. It just can pick any object from the bin that is never seen before and just drop it very reliably with something like 96%. Performance. So this is very exciting. One of the things that's the most exciting about this is that the robot needs to kind of learn how to develop strategies to do a good job at what it's doing. So for example, this is like a complex object, and it kind of learned that it needs to singulate the objects first and push things around so that it can actually grab some of the pieces. This is not something we've programmed. This is something that was completely emergent from the training process. It would be very complicated to try and program a robot to actually do that and have the decision logic that leads to this. But this emerges completely entirely by itself because we're really data-driven. We're really driven by solving the task. So here's another example where the robot was initially failing to grab one of the objects, and then it simply retried. And that's also not something that we programmed into the robot. The retry behavior is something that was emergent because, again, it's only motivated to solve the task. And the only way you can make that work is if you reason about both the the actuation and the perception and your estimates of both jointly. This is the kind of stuff that also enables us to really think about the world in different ways, not just about reasoning about objects and things like that. I know in the food world, you have to reason about liquids, and you have to reason about granular media like beans or things that are not object-like, right? So if you look at a classical perception system, a lot of things are about finding an object and picking it up and understanding what the object is. If you're dealing with something that is amorphous like this, all that goes out the window, and you have to reason holistically about the material. So we've been, experimenting with things like this, where we learn jointly how to perceive things like beans, or we use beans. We wanted to use water, but then we didn't want to destroy the robot. We weren't sure it was entirely, waterproof. So beans were very convenient proxy. And we can reason about those quantities by just letting the system train on purely the outcome, and then reason about what it sees in a completely implicit way, basically trying to pick up the material and based on the task that it wants. So it basically learns only what it needs to know about the task to succeed. So key takeaways, we have new tools. Deep learning is one of those. It's not the only tool in computer vision, but it's a very significant new advance, and it's something that people who are interested in understanding the semantics of the world should really be paying attention to. It enables us to reason about things that are not necessarily the kind of objects that we are used to see, and that's good news. Closing the loop between perception and actuation, I think, is the only way we're going to be able to really reason about the real world in unconstrained environments. Like we really need to really understand things jointly. We don't develop our visual system as humans independently from the real world that we interact with. It's really the interaction that drives our perceptual system, and it should be the same for robots. So I'm very excited. I'm mostly here to learn because, food robotics is kind of a new area we haven't really worked in, but I'm interested in sort of scoping where are new problems that can be solved with techniques that really try to push the boundaries of where robotics can go via perception, via understanding, and via more semantics. If you are interested, feel free to reach out. Thank you.
Yeah, so hold on to that.
Happy to.
And Gary Marcus on the path to AGI. I think I know where you might stand on that, but I'm curious to hear it directly from your mouth.
This is way far from AGI. We're not talking about intelligence here. I think the intelligence would really be the layer on top of all this. Once you have the ability to control things and interpret the world, the real intelligence is really what's coming on top. And so enabling this level of low-level basic perception and actuation, the kind of baby level or animalistic level of proficiency is what would enable us to start working towards AGI. This is not intelligence by any stretch of the imagination. So I'm always hesitant to go into the AI speak, because really what we're doing is so much simpler, especially in robotics. Our robots are really dumb as hell, and as we all know, we're really nowhere close.
Other questions?
So you talked about positive reinforcement as the robot picked up the object correctly. I'm sure that's an analog for something else. Was there some observation or vision system that confirm that it was picked up correctly, and then that got built
Yeah.
into the
Yeah, so
algorithm?
we've verified that the object was picked up by simply looking at the object once it's in the gripper, and you can just do simple classical computer vision techniques to determine whether the object has been picked up or not. So the verification as to whether you succeed or not is a simple computer vision task. Once we have that information, we feed that back to the entire system using deep reinforcement learning. So it's kind of the class of techniques that were used in AlphaGo. If you've been following the system that beats the Go grandmasters recently, or all this it's a way of expressing machine learning problems that have this delayed reward, where you only reward it at the end for completing a complete continuous action that is positive, and learning that in a completely, based on these very simple rewards, learning that perception corresponds to that action, and this is the right action to take given that visual input, if that makes sense.
Right here.
What drives your research? Because you don't have a domain or vertical that you focus on. So do you just pick like general problems to work on?
Yeah, we try to really be very general. The whole, picking and placing is kind of the bread and butter of all sort of ARM-based systems. That's one of the bottlenecks for all of robotics, right? If we could reliably pick objects and put them anywhere, that would be, a very powerful thing for a lot of implementation of robots in the real world. We're looking at navigation as well. Looking at better ways of interacting with humans and with the real world in terms of navigating in complicated situations. We're looking at locomotion because it's a very good testbed for a lot of very broad classes of algorithms. So little quadrupeds running around. And it's always a crowd pleaser to have little robots that can run and jump and do tricks. So we're looking at very fundamental pieces of the robotics space because, frankly, I think a lot of those don't have good solutions, and we really think that we need to improve the basic building blocks before we can start putting them together. And the story of how do you put things together is still to be written, I think, and that's what I'm alluding to in terms of closing the loop and having a continuous system that improves itself basically on the fly, jointly based on its experiences, based its sensory input, and everything that it is that makes its embodiment essentially.
Oh, right here.
Is there the algorithms you have developed for this robot, can it be used for anything else? Is there an...
Sorry?
Can the algorithm be used for anything else? Can it be applied for other applications? Is it
So
generic enough?
The algorithm that was developed for the grasping task is extremely generic. The only constraints that you have is you need to give it a reward at the end. So you need to have a way of verifying that the action that you took was successful. And it also needs some level of bootstrapping. So for example, for pick and place, just commanding the robot to just grab at random actually succeeds some of the time. And it's usually one of the challenges of those kinds of iterative learning systems is that you need to prime them with something that is not completely random. Otherwise, you never succeed. And then it can't learn, it can't progress. So you need to give it some hints as to how do you do the job in an approximative fashion. And once you have that and you can turn the crank and learn much faster, you can basically apply it to any sort of robot behavior that you can think of. The one caveat may be if your behavior contains a lot of steps. Right? If it's a very complex behavior, this is kind of a one-shot thing. If your robot is about making coffee, that would imply a lot of steps along the way. You might need to do something a bit different to sort of enable those steps to happen along the way and not just get the reward at the end.
I think we're out of time. We're going to move on. Thank you so much, Vincent. Big round of applause, please.